This is the Pearson Further Maths Core Pure Paper 1 exam from 2020. It's based on these two books in case you get as confused about all the names of the different exams as I do. So yeah, I just remember it's the two green books with the butterflies on. Anyway, let's make a start. So you've got a calculator, remember, and it's an hour and a half long, which is plenty of time. You've also got a formula book, which we might use occasionally. If you see that this is a root, then of course this is a root. That's the first thing you should write down. I think you even get a free mark just for writing that. And then what I decided to do from here was use a bunch of roots, things that we know from the other chapter in the year 1 book, which is that if you times the 3 roots together, if you call the other root alpha and times the 3 together, you get minus q over 3. It's this one over this one. And then, I mean, we can sort this out, right? These two multiplies to make 17. You can check if you need to, and you get that. But then likewise, the sum of each pair of roots multiplied makes this one over this one. So alpha times this, plus alpha times this, plus this times this, makes 57 over 3, which is of course 19. We already know these multiply to make 17. Something nice here happens, right, where this minus alpha cancels with that plus alpha, and so you just get 6 alpha plus 17 here, and let's move the 17 over to get 2. And then divide by 6 and you get alpha as a third. This is a positive because of course the roots are in doubles here, so it's positive. The triples make a negative there. And then of course we just keep going, right? So we found alpha, so that's fine. We could draw the Argand diagram now, I guess, because we've got all 3 roots, which is cool. The laziest Argand diagram of all time, but okay. Not even sure you'd pick up 4 marks for that, but I'm assuming that's pretty trivial for all of us. And then of course the sum of the roots independently is this one over this one, again with a negative because they're just single roots here. So root plus root plus root is negative p over 3, but we now know alpha is a third, so we'll just shove that in. I think I did quite a lot of stuff here. I times everything by 3 to make this a third become a 1. Again, there's cancelling here, and then 3 plus 3 is 6, times 3 is 18, and so we get this, and then p is minus 19. Go back to this, we already know alpha is a third, so we can find q is minus 17, and we have a relatively nice question done quite quickly, which is good. Question number 2. There's only 7 questions on this entire paper, which is just how Further Maths likes to roll. As soon as you see an integral with something times something else on the bottom, you should probably immediately think partial fractions. Now first we just need to pick up this 1 mark. It's improper because the upper bound is infinity, so that's cool. Prove that this equals this. So again, thinking partial fractions. So we're going to write this like this, just splitting this up here, and then of course you can multiply this to that, multiply this to that, and then just get 1 equals a times this plus b times that, because all the denominators will just cancel out, so it doesn't matter. Comparing the x's on this side, we have 0 x's. Over here we have 2a plus b x's, and comparing the numbers we have 1 equals 5a. So a is a fifth, which putting in here means b is minus 2/5, and then we put that back into here and we say this integral is the same as this integral. But of course we can integrate these two things separately if we wanted to. That would be fine. I think that's exactly what I've done. So a fifth log of x here. They like writing log with this ln symbol, which is trash, but we'll just go with it anyway. Here, this 2 cancels because if you think about differentiating this, this 2 would come out to make a 2/5, which is right here, and then you just get log, you get 1 over this thing here, which is there, so that's good. Here, of course, we can follow log laws and say this is a fifth log of this one divided by this one altogether. And now we're just going to need to substitute in infinity and 1. Now, when we put infinity into this, imagine what happens to this fraction when you send x to infinity. You're just going to get essentially infinity over 2 infinity. This plus 5 is going to matter less and less, which you can just think of as being a half. I think the exam scheme would like to see something like this written down-ish. But anyway, you can say that this is a fifth log of a half when you put in that. And of course, when you put in 1, you get a log of 1 over 7, I believe. So it becomes this. I wrote this. I decided here to write. I know you could just do a half divided by a 7th and just sort that out. I chose to write a half as 2 to the power minus 1 and then put the minus out front. And likewise here, 7 to the minus 1, put the minus out front to cancel that minus. And then of course, you can just swip these over and say it's a log of 7 divided by 2. With a fifth out front, and we should get the answer. A is a fifth and b is 7 over 2 should be our answer. Good, so we've got some polar coordinate stuff to do here. First thing to do is look for the intersection between C1 and C2, I would think, so let's just set this equal to this. I have expanded out the 3 already. I tidied up, of course, this means sine of theta is a half. You should know without a calculator that means that theta is pi over 6, and of course you should also know, hopefully the other one is 5 pi over 6. You can draw the graph if you need to get that. I'm just telling you that this is it. And then to work out the area in polar coordinates, the integral isn't a normal integral, of course. It's a half integral r squared. between two lines. So what I'm going to do is integrate between theta is pi over 6, which is over there somewhere, and 5 pi over 6, which is over there somewhere. And I'm going to integrate C1 between those two things using this formula to get me all of the area above these two lines. And then integrate C2 between those two things to get these little two areas here, and of course take away. Now I'm integrating between the same two lines here, so I can actually just move those integrals together. So I've got the integral of the first one between those two lines and the integral of the second one, but I can just put them together with a minus because I'm just doing C1 minus these two little bits inside of C2, and I can just put them together like this, a half out here because of the formula, and square them again because of the formula. Okay, so let's square these things out. We get this. When you square that one out, you get this. And when this becomes a 9, square that one out from 1 minus 2 sine theta minus, or sorry, plus sine theta squared. But of course, this minus 9 changes all of that, which is cool. Simplify that up. And the only thing that's hard to integrate here is the sine squared. That's quite a hard thing to integrate. You want to use your double angle formulas to do that. This isn't given in the formula book, but in the formula book you do have the compound angle formulas, which you can set A to be equal to B on, and then you can get, after a bit of rearranging, you can get to this formula eventually, which you'll have seen lots of times before. You can actually use the other formulas. You can get sine 2 theta here instead if you want to. I just chose this one because it's the one that popped into my head straight away. And so I just replaced this here. So 8 lots of this is 4 and 4 lots of those. So I've got a 4 here. It's already a minus actually, so that minus changes to a plus, and then this minus, this becomes a minus to be minus 4, which I've taken away from the 8 there. And this all looks integrable now, which is good. I can integrate this, I can integrate this, I can integrate this. I'm not sure. Oh, I took out a 4 here to make this into a 2, that into a 5, and that into a 3. Very intelligent. Okay, I mean, not really, yeah, sure. This integrates, cos integrates to sine, of course. Sine integrates to minus cos. Of course, I need a half out front here because this 2 would differentiate and cancel that out, and then minus 3 theta. I've been very lazy here and just gone straight to the mark scheme for the answer because I honestly couldn't be bothered to type this into a calculator. If you want to test yourself, do this without a calculator because it's quite fun, but I didn't want to waste your time too much doing that since it's completely unnecessary for this particular exam. But yeah, you put the numbers in using a calculator and you'll eventually get this thing out, which is in the form that they wanted, which is good. Question number 4 then. So we're actually almost halfway, I guess. 3 out of 7 questions done. I don't like this form, so I just write it like this every time. It's the same, obviously. I just like vectors. I think they're more clear. I get less confused. Find the Cartesian equation. Now, I know there's a more intelligent way of doing this, but this is the way that I remember it. And I don't teach a lot of vectors, so I'm not too well versed in the other methods. But the way I did this is just write the x equation out, write the y equation out, and write the z equation out, so just reading the top line, second line, and bottom line. If you rearrange the x for lambda, say, and then write out the y line and the z line, and then just shove this lambda into each of these two equations, you get this, which I can simplify to make these two things. I'm doing this quite quickly, but hopefully it's not too complicated to follow. And then what I can do is I can just rearrange one of these for mu, so I think I chose to rearrange this one for mu, double it, I guess, and then just shove that for mu into here, and we end up with an equation just in x, y, and z, which is the Cartesian equation. I know there's a fancier way to do that with like dot products and stuff, but I honestly can't be bothered to remember those things when I'm not actually teaching them, so I just did this the boring algebraic way because I know I'm not going to mess it up. Okay, line L has equation this. Again, the easiest way I think to do this is to turn this into vector form, and then do some stuff with the vector forms, but I just spent some time working out this, so I just decided to do this in Cartesian form with this and this, which again isn't too bad. What you can do is you can just look at the left-hand side of this equality here and rearrange for either x or y, it doesn't matter, and then shove this x into here, and then look at this bit and do exactly the same thing. So I'm sorry, rearrange for x properly there. Look at the second bit, rearrange for x or z or y, it doesn't matter again, I did it for z. And all I have to do now is shove this x rearrangement into here and this z rearrangement into here, and I end up with an equation just in y, which means of course I can solve for y. I've skipped some steps here, but it's just a linear equation, so I'm sure you can follow it. You get y as this, which of course then you can just shove into here to find your x value, and then shove into here to find your z value, and you have the 3 coordinates. There are probably better ways of doing that. I mean, there are better ways of doing that. Making it vectors would have been easier, I think, but I don't really care. Last bit here, plane has this equation, so this is in the dot form. I can't remember what its actual name is. I call it the dot form in my head. Is it the normal vector form? I can't remember. This is the normal vector to the plane, isn't it? I can't remember the names of things. Can't remember anyone's names. Anyway, so what we can do is we can write this in the same form. So this is xyz dot 412 equals 10. XYZ can be represented by r in the same way that it was represented here. And then we can just say, okay, well, the angle between them is the two, I think I wrote this one like this, is the two actual direction vectors dotted together equals the magnitude of each multiplied times cos theta. So that's the formula that you learn for dot products. So we can do this dot that equals the size of this one, which is 16 plus 1 plus 4, which is root 21, times the size of this one. Magnitude means we just square root to the end as well, obviously. This is 8 minus 1 plus 6, which is 13, and we divide by these two and type that into calculator, do cos inverse, and you get this number here very roughly. Good. Question number 5 then, all about differential of things. I'm not sure I did this first question in the most efficient way at all. I think there was a better way of doing it. What I decided to do was just, I decided to black pen, red pen it, essentially, which is, what I mean by that is I tried to find d2x by dt squared, sorry. So differentiate this. Now, of course, to differentiate this becomes d2x by dt squared. This one becomes minus 5 dx by dt, because you've differentiated this kind of wrong. It's implicit differentiation. I'm sure you guys follow. And then this is 10 dy by dt, and then this obviously just goes away. And then what you can do is you can substitute in what you've been given for dx by dt into here, and what you've been given for dy by dt into here to get this. And then, of course, you can just tidy all of that up, which eventually gets you to here. And then this is what I mean by black pen, red penning it. I essentially took this and decided to just make this backwards. So it has an equals 50 over here. So I decided to move everything over to this side except for 50 of these to make this, if you see what I mean. So add 16, we get this. You see what I mean. So I've got the 50 now, and then I decided to make the 5x, which means making this into a minus 10x, just to put a 5x at the end. And then magically this bit here is exactly, I think, 2 lots of this thing here. So we arrive at exactly what they wanted us to show. I think starting with this left and just, there were lots of other better ways of doing that, but I thought that was a more interesting way, at least for me. Okay, so cool. Finding the model, find a general solution for x. So we've got this non-homogeneous, I think it's called. Again, I can't remember any of the proper names of things. I just know how to do things instead. So we need to change this into a homogeneous equation by changing that to 0. And then we get, I think, what's called the auxiliary equation, which is this. We solve it, which gives us complex roots. So then we need to remember if you have complex roots, the general equation or general solution is in the form e to the minus this t times a cos of this t plus a b sine of this t. So it looks a bit like this. That's the general solution. But of course, we solved for equal to 0 when we should have done for 50. So what we need to do is we need to say, okay, well, we need an extra bit. I think it's called I think this is the complementary function. This is the particular integral or something like that. What we need to do is we need to let x equal lambda, because this is just a constant. So this is the form that we need to use. And then we just let x be this, but if you differentiate that twice, you get 0, obviously, because it's just a constant, and this is 0 as well, so you get 5 lambda equals 50, just substituting x into here. 5 lambda equals 50, which means lambda is 10, and then you just pop the 10 on the end of this, and we get our actual solution, or general solution, until we have the limits, which we'll put in later. Okay, and then we need a general solution for y as well. There's a couple of ways you could do this, I'm sure, but what I chose to do was just look at, I just chose to differentiate this, I think. Yeah, I did. Now you need to use product rule here. So this minus, you differentiate this one first, which is of course just minus e to the minus t, and then leave this one alone. And then you leave this one alone and differentiate this. Cos differentiates to minus sign, you put the 2 in front, sine differentiates to cos, you get that. 10 goes away, of course. And then what I decided to do was, okay, say, well, dx by dt, which is all of this, is equal to minus 5 of x, so I put all of this x into there, plus 10y minus 30, and I decided that I could rearrange all of this for y. Again, probably not the most efficient thing to do here, but I just did everything the way that I didn't really sit and think about any more efficient ways. I just did it the first way that popped in my head every time. I have plenty of time. So Okay, here what I did was I think I times everything by e to the t just because I wanted fewer e to the t, e to the t to make all of these e to these go away and just add a couple to the end terms, which seemed easier for me to deal with, just to write down. Anyway, then I grouped together all of the cos. I know this looks super horrible with the equals here, but apologies for that. Grouped together the cos, so I've got one of the coses here plus 2b over there. I've actually got minus 1 a cos there and 2b's over there, so that's 2b minus a coses. And then the sines, I've got minus b minus 2a of the sines. But now on the other side, when I expand out all this, I can add 5a to both sides to make that into a 4a, and add 5b to make that a 4b. And I think I end up with this. Group these two things together, of course, move them to the other side. At this point, you can divide again by e to the t to put that, or you can, of course, as well, I guess, what did I do here? Factorize out a 1/10? Oh, divide by 10, sorry. Divide by 10 to get and then divide by e to the t. And I think I end up with a horrible equation in terms of y, but I think it is correct. And then we just put in some numbers. So this is the easiest bit of the question. Put in x as 2 into our I think actually I chose to start with here. Put in y as 5, put in t as 2. Of course, we should know cos of 0 is 1, so we keep this. That becomes a 1. We lose this because sine of 0 is 0, so we just end up with this bit here, where e to the minus t is 1. Plus 8 equals 5, because y is 5. And then we go back up to there, and we can do the same thing with x is 2. This is good because it's a simpler equation, and this just goes away, as I've said. So we get a as minus 8, and then we just put a as minus 8 into here, and I think we end up with b as 1. And so then we can substitute minus 8 and 1 into there, and we get our two equations. We can divide this one by 10 when we do that, when we put in the numbers into here, and we get this, which I think will be our two answers for our particular solutions, or final solutions that we've got here. Scientist thinks the chemical reaction will have stopped after 8 minutes. Explain why this is supported. This term is the important bit. Like when you make t quite large, e to the minus quite a large number is you're basically just getting to 0. So essentially, this fluctuating term, which will keep fluctuating all around the place, but because it's being squashed down by this very, very small term, x is basically just going to equal 10 when t is very large, and likewise y is basically just going to equal 8. And the fact that x and y are staying about the same, they're the amounts of compound in the chemical reaction, means that not much reaction is happening anymore. So you just have to say when t is large, this happens, and the reaction is mostly stopped or not really doing much anymore. Something to that effect. Not a chemist, don't know. Anyway, so here we've got a nice question because I like this sort of thing. We've got proof by induction of a series formula. So okay, we just set n to be 1, and if n is 1, then you're just literally putting r is 1 into here. And then of course we can put n is 1 into here, and we see that the two answers are the same. So it works for n is 1. And then we assume that it works for n is k, i.e. we assume that this is true. And then what we do is we say, okay, can we show that it's true for, or let's n equals k plus 1, which gives us this statement, and try and show that it's equal to when you put k as 1 into here. So let's just start with this. Well, the obvious thing to do is to say that this sum is the same as the sum from r equals 1 to k, plus the term when you put k plus 1 into here. So when you put k plus 1 into here, you get 3k plus 3 plus 1, and k plus 1 plus 2. And I'm going to simplify that up, but I'm also going to use the assumption step here to replace all of this with this here. So I'm going to replace this with this here, and I'm also going to tidy that up, and I think we get this if I do that. But of course, this has a k plus 3 in common, so I factorize that out to leave me behind this bit at the front and this bit here. I can expand this out and tidy it up, and we get this, and I can factorize that back to get this. And remember, that's equal to the sum up to k plus 1. That was the first thing I started with, and I got all the way to here. But of course, I can write this as k. If I underline the red bits like this, we can see all that's happened is this k plus 1 has gone here, 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 which is the same as this n going here, here, here. And we end up with the correct thing. So we've shown that it's true for n is 1. If it is ever true for n equals k, then it's true for the next one, being whole numbers, and so therefore it's true for all values. And you just have to write something to that effect. Yeah. Good. Next bit. So again, for odd integers, prove this thing. So we just start by putting n as 1 in, and it works. You get 15, which is obviously divisible by 15. And then you say, okay, let's just assume that it's true for n equals k. You could say assume true for n equals 2k plus 1, because of course you're proving this for the odd numbers, but you can be a bit lazier and just assume that it's true for n is k, and then assume this, and then show true for k plus 2, because you want to go to the next number, which is odd. And of course, if I have shown 1 is the one that's true, the aim will be to prove this, and that therefore, if it's ever true for n, which I know it is for 1, it's true for the 1, 2 further along, which means it will be true for 3, and then 5, and then 7, and so on. So I think I'm good to do this, and okay, good. So we can put in k plus 2 into here, and now of course this is 4 to the k times 4 squared, because you'd add the indices if you're multiplying bases. So 4 to the k times 4 squared is 16 times 4 to the k. Likewise, this is 25k, 5 to the k, this is 36, 6 to the k. And what I can do here is I can just take out 16 of each one like this. So I've stolen 16 from here to put them into here, and 16 from there to put them in there. Now this, by assumption step, is divisible by 15. So that's no problem. This, and I probably should have written out another line here, but I'm just going to say it out loud. This is a 9, which has a 3 in it. And this is a 5 to the k, which has a 5 in it, assuming that k is bigger than 0. Which means this has a 3 in it and has a 5 in it, which means it's made up of a 15. It has a 15. You could also factorize out 5 to make it 45 lots of 5 to the k minus 1, which makes it more obvious that it's divisible by 15. But what I've said out loud I think is enough. Just write that down. And this likewise has a 5 in it here from the 20, and a 3 in it from here, from the 6 to the k. So therefore there's a factor of 15 in here, because there's a 5 there and a 3 there. And so all three of these terms are definitely divisible by 15. Which means that the whole thing is divisible by 15, and that's what we were trying to show. So we write a statement that says roughly the same thing. I should have done some more proper maths here, but I think what I said out loud is also enough. This question was quite funny. What I decided to do was divide by 1 plus t to make it into the form where I can do the what's it called? The integrating factor, of course. So to do an integrating factor here, you do e to the power the integral of this function here, and you multiply everything by that. But of course I can just do this integral first. This is log of 1 plus t, but the integral of log of 1 plus t, this is the integral of 1 over 1 plus t is log of 1 plus t, but e to the log of 1 plus t is just 1 plus t. But if I multiply all of this by 1 plus t, then I just get this, which is, I don't know why I wrote this equation out twice, I haven't done anything. I'm timesing this by the integrating factor, which is this, which is just 1 plus t, because that cancels. So I multiply this by 1 plus t, and hilariously get back to what I started with. So I've achieved nothing, except knowing now that actually I've just missed something, which is that this here, you can just integrate, because it's already of the form like u dashed v plus v dashed u, in the sense that it's just this. It's the reversal of a product rule for differentiation. If I differentiate this via product rule, leave this alone, that becomes dp by dt, and then differentiate this for a 1 and leave that alone, and you get this. So it wasn't a complete waste of time. The fact that it went back to what I had before just showed me that I was missing that this was already integrable. Of course I can integrate this side here, or both. I mean, I can integrate both sides really to cancel this and integrate that side. This of course just expands out to make something very integrable, which we integrate. I've put a plus c here because I've got some limits to put in, I guess. Yeah, when t is 0, initially there are 5,000. So when t is 0, p is in thousands, so p is 5. Just make sure to read that carefully. Put those two values in, and I think we get c as 5, because of course cancels, yeah, it just goes away, and you just get p equals, yeah, cool. So c is 5. Good. So that's determine the course of the model of the number of bacteria 8 hours into the start, so we just replace t with an 8, so you type all of this into a calculator, divide by 9 at the end, you get this. Again, p is in thousands, so that's going to be actual number 10,227 or something around there. Find according to the model the rate of change, so we're looking for dp by dt 4 hours in. So I have an equation for dp by dt, and I can just substitute in t as 4, but I would also need to substitute in p. So what I decided to do was use the same equation we just used here to find p after 4 hours. So I just put in 4 into this equation that we just used to find, I don't know why I wrote that out twice, so just substitute this, what am I doing, to get this, which means p is 4,627, I guess. And then I can go back to this equation and substitute in that value for p along with t is 4 to find dp by dt when t is 4. And I'll just type that into a calculator, take away this, and then divide by 5, and I get this, which again times by 1,000 to get this as our actual number. State and limitation of the model. Well, the model doesn't seem to have any built-in limitations for, in real life, the bacteria. This is just the standard answer, isn't it, that you write down every single time for the 1 mark. In real life, the bacteria would slow down, the growth would slow down at some point due to external factors like size of the petri dish or lack of food or whatever. The model doesn't seem to have that built into it, so over time it's going to be limited because it's just going to show growth, over more and more growth. I think that's the entire paper, so thank you so much for watching, and I'll see you next time.